Okay guys, welcome to our next lesson, section 4 day 2. Today again we are continuing to look at logarithmic models. So we are going to be looking at real life situations with 3 different formulas and how the logs and the mathematics apply to those situations. Our first one is one that we did in the last lesson, our Richter scale equation. And remember, the Richter scale measures our earthquake intensity, or the power that is released. So here is my equation when I'm dealing with earthquakes. It is m equals 2/3 times log of E over E sub 0. And m, the letter m, represents the magnitude on the Richter scale. The letter E, so this E in the numerator, represents the energy released by the earthquake, and we measure energy in joules. And E sub 0, we always use the value 10 to the power of 440 for E sub 0, because that's going to be a very small reference earthquake, so that's why we always plug that number in. We're using that as our base number to measure all other earthquakes. And so here is my earthquake example. We have the atomic bomb dropped on Nagasaki, Japan on August 9th, 1945, released about 1.34 times 10 to the power of 14 joules of energy. What would be the magnitude of an earthquake that released that much energy? So again, we're now going to compare the energy released in the atomic bomb to the energy of an earthquake if it was just as powerful as that atomic bomb. So let's set up our equation. My magnitude would be 2/3 times log. Instead of E, the energy released is 1.34 times 10 to the 14th. So that's what I'm going to plug in. 1.34 times 10 to the power of 14. And then remember, for E sub 0, I'm always going to plug in my value of 10 to the power of 440. So there's my equation set up, but now please be careful of how we write this in the calculator, and that's why down here I have our calculator set up. All of our fractions need to go in parentheses. So the 2/3 has to go in parentheses, and then what I am taking the log of also has to go in parentheses. Now my numerator needs an additional set of parentheses around it to make sure our order of operations is correct. So in my calculator, I'm going to put 2 divided by 3. Again, notice we have that in parentheses. My multiplication symbol, log. Notice I have a general parentheses for my log, but then I also have a second set of parentheses for my numerator. So then I would have 1.34 times 10 to the 14th in my second set of parentheses. And my numerator does not need my denominator does not need its own parentheses, but if you wanted to put 10 to the 440 in parentheses, you certainly could. Okay, so now we have our equation and how we should be entering it into the calculator. And when we put all of that into the calculator, I end up with m equals 6.5. So of course, this is measured on the Richter scale. So to answer our original question, the atomic bomb, if we were to compare that energy to the earthquake Richter scale, that would be a 6.5 earthquake on the Richter scale. So a pretty powerful earthquake, the atomic bomb. All right, let's go to our next example here. Also looking at our earthquake formula. A moderate-sized solar flare observed on the sun on July 9th, 1996, released enough energy to power the United States for almost 23,000 years at 2001 consumption levels, 2.38 times 10 to the 21 joules. What would be the magnitude of an earthquake that released that much energy? So again, we're looking at solar flares on the sun, but we're comparing them to earthquakes here on Earth. How powerful is that solar flare on the sun? So I'm going to start with my formula. M equals 2/3 times log. For E, they tell me that the energy released enough energy was 2.38 times 10 to the 21. So that's what I'm going to put in my numerator, 2.38 times 10 to the 21. Remember, for e sub 0, I always use my value of 10 to the power of 440. Please be careful. We've set up the entire equation. Now it's just putting it into the calculator. But please remember to put all of my fractions in parentheses. So I'm going to have 2/3 in parentheses. My numerator gets an extra parentheses. So 2.38 times 10 to the 21st. And then I have my 10 to the 440. If you wanted to put your 10 to the 440 in extra parentheses, you could. And so once you enter all of this into the calculator, you end up with a magnitude of 11.3 on the Richter scale. So we are saying that this solar flare is actually much more powerful than any earthquake we've ever experienced here on Earth, right? Because our maximum Richter scale, we usually consider it 9 because we haven't had an earthquake more powerful than that. So these solar flares are extremely powerful on the sun, and there is an example of how we would use our formula for that comparison. Now let's go to our second equation that we're going to be using today, which this is a new one. This is the equation for rocket flight. And so this equation is going to show the velocity of a rocket at burnout. Now by burnout, we mean when the fuel supply is gone. Okay, so when all the gas, when all the fuel is gone, how fast is this rocket still traveling? And so this is the equation that we're going to be using. V equals C times ln of Wt over Wb. So V stands for the velocity. Okay, this letter V stands for the velocity. Our letter C stands for the exhaust velocity of the rocket engine. Wt stands for the takeoff weight. So how much does this rocket weigh when it takes off? And Wb stands for the burnout weight. How much does this rocket weigh when all of the fuel is gone? Because of course the takeoff weight is always going to be more than the burnout weight, right? Because if nothing else, you're losing fuel. Okay, and fuel does have a weight to it. So let's go ahead, let's use this equation for our rocket velocity example. A new solid fuel rocket has a weight ratio, Wt over Wb, equals 19.8, and an exhaust velocity, c, equals 2.57 kilometers per second. What is its velocity at burnout? Compute the answer to 2 decimal places. So here's our equation for velocity at burnout. So all I need to do is fill this in. I put V equals my letter C. They tell me right in here in the problem. So I can just put 2.57 times ln. Remember, ln is just my natural log. Okay, so when we say ln, we mean natural log. And in your calculator, it is next to the number 4, okay? So that ln symbol is just to the left of the number 4 in your calculator. Now for Wt over Wb, they do not give us separate values, but they give us the entire ratio. They say Wt over Wb is 19.8, so I just put 19.8 here, because that represents the entire ratio Wt over Wb. So now I can just put all of this pretty easily right into my calculator. You don't have to worry about any extra parentheses or anything like that. So what I end up with for my velocity is 7.67, and because the question used kilometers per second, that is going to be my units. The velocity of this rocket at burnout would be 7.67 kilometers per second. So still moving extremely quickly. Okay, guys? So that is our velocity burnout formula. Let's go to the last formula that we're going to do in this lesson, which is our chemistry formula. Okay? So this chemistry formula is going to be used for homework question number 20. All right, so the one that we're going to do here in the PowerPoint is number 19 to show you guys an example of what that would look like. Now the formula here for chemistry is going to be the pH scale formula, which looks like this. pH equals negative log of H plus. Now that H plus symbol represents the hydrogen ion concentration. Okay? Pure water has a pH of 7 because pure water is considered completely neutral. Okay? If something has a pH of less than 7, then it's considered acidic. And I'm sure, right, in science, you guys have talked about acids and bases. So if there's a pH of less than 7, it's considered an acid. If it's a pH of greater than 7, it's considered a base or basic. Okay? So here is the chemistry formula and how we are going to interpret that pH. So let's go ahead and use this in our last example for today. So homework problem number 19, which will be very similar to number 20 for you guys. Compute the pH of each substance listed given the indicated hydrogen ion concentration. Also indicate whether it is acidic or basic. Compute answers to 1 decimal place. So notice we have example A for seawater, example B for vinegar. Here is my equation. So I'm going to draw my line down the middle to split these up. So for seawater, I'm just going to enter my equation. pH equals negative log. If this is my hydrogen ion concentration, I'm just going to plug that in for H+. So negative log of 4.63 times 10 to the negative 9. So that's it for setting up my pH equation. So now I can enter all of this right into my calculator. And so what I get for the pH of seawater is going to be 8.3. So there's my final answer for the pH of seawater. Now since 8.3 is greater than 7, that means that seawater is going to be basic. So make sure that you include both parts of the answer. You need to tell me that the pH of seawater is 8.3, and then you also need to tell me that seawater would be basic. Now let's go over here to vinegar, and let's set this up here in example B. So pH equals negative log. All I'm going to do is plug in my value, 9.32 times 10 to the negative 4. I can enter all of that right into the calculator, and I end up with pH equals 3.0. So there is my pH of this vinegar. Now, this pH is less than 7. And so if it is less than 7, it is considered acidic. And that makes sense, right? Because when you think of vinegar, balsamic vinegar, things like that, they're acidic, right? They have that little bit of tartness, vinegariness, acid to them, okay? So my seawater has a pH of 8.3 and it's considered basic. My vinegar has a pH of 3 and it's considered acidic, okay? So there is my last example. We did all 3 of our equations. Here is your homework for today, guys. So this is in Google Classroom. Please make sure that you complete these. Notice it's only 4 problems. And then you're going to upload photos of your work to Google Classroom, okay? If you have any questions, just type those right into the comments in Google Classroom, and I'll be happy to answer them for you. All right, guys? So thanks for joining me for this lesson, and I will see you guys for the next one.